So in this particular video, we are going to derive the Lagrangian density for our Klein Gordon equation. So in our first video, we had derived the Klein Gordon equation, but what we are going to do in this particular video is that we are going to derive the Lagrangian density, and we will see that how from the Lagrangian and plugging that Lagrangian into the Euler-Lagrange equation, you will get that exact formula of the Klein Gordon equation. So we are going to do that. First of all, we have to derive the Lagrangian of that particular Klein Gordon equation, so you can say that Lagrangian for that scalar field, because in quantum field theory we only deal with the different types of the fields. There are vector fields, tensor fields, scalar fields, different types of fields. So we are going to derive here particularly for the Klein Gordon equation. What's its Lagrangian density? First of all, you should know that what exactly this particular Lagrangian density is. You have heard about the Lagrangian, not the Lagrangian density. So what's the difference between this particular Lagrangian and this Lagrangian density? What is the difference between this? So the difference is like that. Lagrangian is written like L, but this Lagrangian density is like a curly L. So you can, yeah, this is the sign for it, but the difference is not between the sign. The difference is that when you define the action, so you have heard about the action, it's the Lagrangian and dt integral from any time t initial to some t final. Okay, so this is our action. So in this particular action, this is the Lagrangian or the Lagrangian density. But in the quantum field theory, there is a slight change in our notations, that we define the actions on the fields. So when we define this, we can have to change our equation. So this equation looks like this, that this action is equal to some t initial to some t final. And what we're going to do is that we're going to substitute the Lagrangian density d cube x and dt. So here this notation, here this particular thing you are seeing is that particular Lagrangian density. So what I am trying to convey is that this particular thing holds on the fields, not on the single particle. So now you have your Lagrangian not only for the single particle but for the fields. That's why this particular action is for fields, because you define the Lagrangian density, not the normal Lagrangian, because Lagrangian is for single particle. And here we defined it for the fields, because in quantum field theory we deal with fields. Okay, so using this particular principle, we are going to derive the Lagrangian C. How we are going? First of all, we define action is integral. I am not going to put the limit. So dt, 1 minute. We have to convert this into the 4 d4x, and here the curly L. So this is your integral. What I'm going to do, I'm going to use a very famous thing which used in deriving the Euler-Lagrange equation from the action, is that the variation in S is equals to 0. What's the meaning of this? So I'm not going to do entirely that what exactly this means. I'm going to just say that suppose that you have two paths here. So let's say there are various types of ways to go from point A to point B, but the path, the natural path that the particle follows, is the path where the slight variation in the path is equals to 0. This means the variation in the action is 0. The slight variation is S should be 0. This means that the particle will generally choose this particular path. That's the typical meaning of the variation of S should be 0. Maybe the end point and the final point, or the first point and the final point is same. There are various ways to go this, but the particle will follow that particular path in which this integral is minimized, or stationary. You can say that the stationary value of this particular action is the path that particle will follow. Naturally, the particle will follow. And that is the meaning of the action. So any slight variation is S should be equal to 0. And that particular thing we are going to do, and we are going to derive that particular Lagrangian from this particular famous thing, that the variation is S should be 0 naturally. Okay, so see how we are going to do this. So we have defined So slight variation in S is equals to integral of t4x, and let's see how we're gonna define this. First of all, let me show you one very important thing, that the Lagrangian is dependent upon q dot and q in the general cases where q is the generalized coordinate. But here in the quantum field theory, the Lagrangian also depends upon, let's say, field phi and the derivative of the field phi with respect to the mu. So this is the Lagrangian which is dependent upon field phi and the derivative of this particular field, and you have to know that what this particular sign is. So whenever there is written like this particular thing is equal to partial derivative of your something, like let's say here we have our field with respect to some x indices mu. So this is the meaning of this particular notation. So you have to use these types of small and short notations because it's very useful in compromising all of that and compressing all of that equations. So you have to know. Okay, so here the Lagrangian is dependent upon two things, phi and the partial derivative of phi with respect to the x mu. So if we take the variation, you have to know some basic things like how to do the variation. If you have taken the courses in the multivariable calculus, you know about this. So I'm going to write it as del L divided by del of phi and a small variation in phi. Okay, so let me erase this, and here plus del of L divided by del mu of phi, and here variation in del mu phi. So now closing the bracket. So this is our integral. Now we have to do some of the calculations. So let's see what we can do. So variation in S is equals to integral of this particular thing. So del L divided by del phi, and here a small variation in phi, plus what I can do is that I can, let me put here the big bracket, okay, x, and here big bracket. So I can take this out, this particular del mu and del mu, and I can take this out, and del L divided by del of del mu phi, and here it should be a small variation in phi. This is a rule, okay, so you can generally prove this rule, and I'm leaving this up to you to prove this. And now close the bracket. Now there are two here. You can apply the chain rule, you can apply the product rule here, that it is equals to the integral d4x, and here del L divided by del phi, small variation in phi, plus if you will apply this here, this is a slight big equation, so let me, okay, so this is equal to plus, when you apply del mu first on this and on this, so it is equal to del mu del L divided by del of del mu phi into small variation in phi, and then plus del L divided by del mu phi, and then here it should be del mu of a small variation in phi. Okay, so this is our equation. Now I'm going to use a very important thing. So let me remind you that this particular thing, this and this is same. Yeah, take time to understand this particular equation and this particular equation, this particular thing is same. Yes, this is same. Just see this, take a time. You can see that here is del L divided by del of del mu phi. You have here del L divided by del of del mu phi, and here you have variation in del mu phi. What I have told you is that you can just plug this out del here, and what you have here is, see, here you have del mu and here you have variation in phi. So both of these two equations are same. Here you have to notice that here the L that I have written here is not a Lagrangian, it's the Lagrangian density. So let me remind us that L is the Lagrangian density, not the Lagrangian. So don't be confused. I'm not writing the cursive L because I'm not used to write this notation, but I'm sorry for this, I have to, but I'm not very used to like this particular Lagrangian. So I'm writing here this L, and this L is not the Lagrangian, this is the Lagrangian density, remember it. Okay, now this two equation, as you can see here, these two equations, what I'm going to do is that I'm going to use a very standard thing. What? So see this. So I'm going to write this particular equation here. Just see this equation. Del mu of del L divided by del of del mu phi and a small variation in phi. This is our equation, and this is equal to these two things. Yes, no, yes. So this is equals to these two things, that del mu of del L divided by del of del mu phi and a small variation in phi, and then plus del Lagrangian density is okay, so del mu phi and here small variation in phi. I want this. 1 minute, here is a mistake here, I guess. I have not written here del mu. 1 minute. Here should be del mu, then a small variation in phi. What I have to do is I have to use this particular equation. So what I am going to do, I can just wrote down this particular equation on the left hand side. So it's like del mu del L divided by del of del mu phi small variation in phi minus del mu del L divided by del of 1 minute del of 1 minute. Okay, so del mu and del L of del mu phi small variation in phi, and this particular thing is equal to this. So I'm going to write it this del L divided by del of del mu phi, and here a small variation del mu and a small variation in phi. You will say why I have written this. So what I'm going to do is that this particular equation, okay, so I'm going to put down the value of this in this equation, what I have said this. Okay, so this particular thing, remember this particular thing and this particular thing both are same. So what I am trying to say is that can I put on this place of this, can I put this particular value? So yes, of course, these two are the same. So I can, what I'm going to do is that I'm going to put this particular equation, see very carefully, this particular equation in the place of this particular equation I'm going to put it. So let's see what will happen. So initially we have our small variation in s, and it is equals to the integral of d4x, and it was del L. I'm going to write the first equation that I have written, del L divided by del of phi small variation in phi, and then plus I'm going to write this particular equation here. So it's del mu. Then you will ask that what is the difference between this and this, because you are seeing that these both two looks like the same. The fact is that here the del mu is acting on both of this particular quantity, understood, but here del mu acts on only del L by del of del mu phi, not on this small variation in phi. Okay, you should understand is that there are difference between these two equations. Here initially I have not operate this particular del mu on this particular thing in this particular equation. That's why there's a difference between, you can't just cut it down and put it 0. Okay, so del mu of del L divided by del of del mu phi and a small variation in phi, this is our equation, and minus of del mu del L divided by del of del mu phi, 1 minute, del mu phi, and here small variation in phi. So this is our equation, and of course it's under the integral. So what I'm going to do is that, see very carefully here, that a small variation in s is equal to integral of d4x. I'm going to separate this. So del L divided by del phi, writing this as the same, and a small variation phi, minus I'm going to put down this particular equation here, which is del mu divided by del L divided by del of del mu phi and variation in phi, this two separately, and plus again d4x what I have said, I'm going to separate this. So I'm going to write this particular equation here, del mu, and whatever the equation is, the fact is that, okay, so the fact is that this particular goes to 0. This particular quantity that I will write, this particular equation goes to 0. So it's not very useful to write down here, but you can say that here what is the criteria that any small variation in phi of t should be equal to 0, and when you put down the limits here, you will see that this particular thing goes to 0. So there is no point in writing this. I'm going to just erase this. Okay, so don't be confused that why I have not written this particular second term, because this particular second term will go to 0. That's why I just neglect it, and I'm only writing this and this, which is here. Okay, now what we are going to do, we are going to operate all of the different things, like del of s is equals to the integral of d4x. I'm taking common del of phi, so del L divided by del phi minus del mu, minus del mu del L divided by del of del mu phi. Here I have taken the common, the small variation in phi. So what I have written, that the small variation in s should be equal to 0. This is what I have written. It means this particular equation, this particular thing goes to 0. There are two ways. First is that this del of phi should be 0, or second, this particular quantity to be 0. Yes, we are going to write this here. Let's see. This is very important. So del L, it means this particular should be 0, del of phi minus del mu del L divided by del of del mu phi equals to 0. Guess what? This is our equation. This is our Lagrangian equation, Euler-Lagrange equation. This is very important. This is our Euler-Lagrange equation. Now we are going to derive the Lagrangian for our Klein Gordon equation. Okay, we have derived the Euler-Lagrange equation of any of the scalar fields, and remember here I am telling you again that this L is the Lagrangian density. Lagrangian density, not the normal Lagrangian that we used in the classical mechanics. Okay, now we are going to derive the Lagrangian. How? So the analogy with the string, so if you have a string, let's say you have a standing wave here, let's say, so we are going to write down the Lagrangian of it as 1/2 mass into v square, yes, and then again minus 1/2 into something like m omega square x. So this is how we define it. This is the kinetic energy, this is our potential energy. For any of the spring block system, you can assume that. So I'm just guessing the Lagrangian. This is not a correct, but I'm just guessing the Lagrangian to be like this. So Lagrangian should be like this. So what my guessing is saying, that I can write Lagrangian as 1/2. Okay, so we are working with fields, so it can be written as del mu phi, del mu phi, del mu phi, del mu phi minus 1/2 m square phi square. Yes, these two equations are not similar, even they are not equal. Okay, because this is dealing with single particle and this is for the fields, but I'm just building an analogy that how we can guess the Lagrangian using some of the simple systems. And this is our Lagrangian. You will say here is m, but here is m square. What the thing here? If you want to just compare, or you can want to build an analogy, intuition about deriving the Lagrangian or just guessing the Lagrangian, you should tell me that why here is m square. So the simplest reason I can give for this is that if you have seen the Klein Gordon equation, there is an m squared term. So that's why to get the Lagrangian and putting into the Euler-Lagrange equation, if I have to get the m squared term, I have to put here m square. That's why I have written here the m square. So let me write it now clearly, m square phi square, and this is our very important thing, and this is our Lagrangian for our Klein Gordon equation. So if you don't believe me, just take the derivative of the Lagrangian with respect to the different thing, with respect to the phi and del mu phi, and check this. you will get the Klein Gordon equation, and I am leaving this up to you to derive the, so I am leaving to derive the Klein Gordon equation. So derive the Klein Gordon equation. I'm leaving this up to you. Just do this on your own, because I have derived Lagrangian. You have to just take the derivative, putting into Lagrangian equation, you will get the Klein Gordon equation. So there is one another thing here, that in most of the books there is a slight different term in the particular kinetic energy, which I'm going to write out and clarify that what exactly this is. So it's 1/2. If you know that how to lower and up the indices in the tensor, we apply any of the particular tensor. So I'm going to put here in this is called nu, you can say that, but I guess this is eta. So let's say this is nu. So this nu is equals to the mu nu del mu del nu phi minus 1/2 m square phi square. So I have just lowered the indices of this particular So if I have to lower the indices, I have to apply the metric tensor here. This is any of the tensor. This is the Minkowski metric generally, and Minkowski metric is, I guess, minus and then plus plus plus, or you can just put plus and then minus minus minus. Both of the conventions are right. Here you will see that when you apply and when you do the product here, this particular things cut out, and you are again left with this particular equation. So these two equations are same. What I have done is that I have just lowered the indices, and to lower the indices we have to apply this. So this is our another form of Lagrangian, but not very famous. This is quite famous and used in most of the books. I told you about this because maybe you will find difficulty about the term here, that what exactly this means, what's the difference between this equation and this equation. So this is my video on deriving the Lagrangian, or you can say that more specifically the guessing the Lagrangian for the Klein Gordon equation. So this is my video. Thank you for watching my video.